All right. So during our last lecture of Monday, we basically started seeing the concept of degrees of freedom and the concept of constraints. Eventually, in the very last part of the lecture, what we did was to introduce also the concept of holonomic and non-holonomic constraints. The former being a sort of constraint that limit the configuration of a system, a mechanical system, while the latter typically constrain the way that a system has to move. Okay, so they are constraints which involve motion. So what we're going to do today is to actually see and carry on some mathematical treatment of this concept, more in depth, and then move on. We will see some example, and eventually we'll resort to definition of degrees of freedom of a system, which is so important for the analysis of a dynamical system. So, without further ado, we can start. We were talking about you. Well, huh? Okay. All right, so allow me to close. It's kind of noisy. Okay, so the topic of today's lecture is constraint categorization. There you go. So, so the first type of constraint that we're going to analyze are the so-called holonomic constraints. Okay, so those constraints typically have this form. So they typically come into this form. That's to say, a vector C of dimension nc rows times one column, so it's a column vector. If you don't see, I can use the projector, but just tell me, no problem. A vector which is dependent on the q's, which are the generalized parameters or coordinates that we have already introduced, and typically time, equal to 0 vector. So what is this, in fact? This is a vector equation. So it's a system. This is a way to write a system of NC scalar algebraic equations. That's a compact way to do that. In fact, we can also further differentiate this type of constraints into scleronomic constraints. So let me write it in capital letters, which is better. Scleronomic. And rheonomic. What's the difference between them? In this one, time does not appear explicitly in these equations. So time t does not appear explicitly. In the rheonomic ones, instead, time appears explicitly. What does it mean, explicitly or implicitly? It means that in these equations, if we have a scleronomic system of constraints, time, of course, play a role, but just indirectly through the q's, which are a function of time, of course. Okay, not explicitly. In the holonomic case, instead, it does appear as a parameter in the equation. You actually see it explicitly. So time does appear. There you go. Where, of course, in this previous equation that we wrote, as we have already mentioned, the Q's have the following form. So Q1, Q2, eventually up to Qn, transpose, of course, where in case of a system living in the 3D space, we have that n is equal to 6 or /7 times nb, where 6/7, as we have already introduced, indicates the fact that we are using 6 or 7 parameters to completely define the position, the orientation of a body in space. Why 6 or 7? Because we can either use one type of parameterization to indicate the attitude, which make use of the minimum number, which is 3 parameters which identify the attitude, like, for example, the Euler's angles, or 7 or 3 or 4, sorry, like in the Euler's parameters, in which we have 4 parameters plus a closing equation. And MB is the number of bodies. Number of bodies. Okay. So these are the parameters. Okay. Now let's make an example of these two, of the scleronomic or holonomic constraints, what they actually look like. So this is the equation. And of course, this is the number of constraints. And C is the number of constraints. Here I'm just writing number of constraints, not number of independent constraints. That's different. Okay. All right, so let's make an example. Let's introduce because we have talked so much about constraints, but now let's actually see one. Scleronomic case. So scleronomic constraints. And to do so, let's actually use a picture. All right, let's see this one, in which we have, let's say, a 2D case. So we have two bodies, usually shaped as potatoes, typically, which live in the 2D space and which are joined by a hinge in point P. Okay, so there you go. Let's write it. We have two bodies. That's between the hypothesis section. We have two bodies, which we denote with the subscript I and J. Into the space. Okay. What else? There is a hinge, a revolute joint, if you want. So they are kind of synonyms, in fact, but in 2D space, we typically talk about revolute joints, but you can use them as synonyms. There is a revolute joint in P. Okay. Where is P? P is here. Okay. Again, we can talk this as a hinge as well. It's a hinge. What we have to do, that's the thesis, we must enforce that the position of point P belonging to the body I is identical at all times. That's the sign, the meaning of the three equals to the position of point P, but belonging to point J. That's what we have to write. Okay, so this is the position. They are in fact two different material points. One actually it's a portion of the body I. The other one is a portion of the body J, and their position must be equal at all times. That's the hinge, because eventually they can rotate. Rotation is free, relative rotation, but position it must be the same. So in terms of let's say vector equation, how can we rewrite this? We have to say that since we have learned how to write this, we can write this as the position vector of the origin of the body I plus the rotation matrix of the body I applied over the position R0 of point P described with respect to the body frame of the body I must be equal at all times to the same stuff, the same quantity, but relative to the body J. Okay? This is what we have to write. That's the vector equation. You see? This is a constraint equation. And you see that, we will see it more clearly right now, but you can already see that time does not appear explicitly in this case. So that's why we are talking about scleronomic constraints here. Okay? So here we have scleronomic. All right. So let's actually write it. Yeah, of course. Thank you. Okay. So if we want to write it explicitly, what we have to write is R1 by J of body I, R2 of body I, and that's the very first part, plus, so what is the rotation, the form of the rotation matrix in the 2D space? We have already seen it. It's very easy. It's cosinus of theta I minus sinus of theta I, sinus of theta I, cosinus of theta I. Okay? This must be equal at all times, as we have said, to the same stuff, but refer to the body J. R1, R2, plus, no, wait a minute. I forgot one part. Nobody said anything. This matrix has to be applied over R0P. Of course. So where R0, 1, I of point P, and R0, 2 of point P, always of body I. Let's actually rewrite this a little bit upper. Here, like so. Okay. And now we have to write the same stuff, but refer to body J. So we have R1 and R2, but refer to body J, plus always cosinus of theta minus sinus of theta, cosinus of theta, and of theta, always J. In this case, we are talking about body J. and then applied over R0, 1P, J, and R0, 2P, J over bar. Okay? So you see, why did I actually also these dotted lines? To make you see that we have two scalars equations. Yeah? And as you can see, as we have already hinted, there is no explicit appearance of time. Okay? So this is actually what a constraint equation looks like, a very simple one. Now we're going to see the case of a reonomic constraint equation. Can I slide it? All right. So example 2, reonomic case. This case, you're going to see, for example, another occurrence. So you see, this is, as you can see in the caption, it's the Canadarm, so it's a robotic arm installed in the International Space Station. Okay. Typically, the way these arms are operated is through imposing a motion to the end effector. Okay, so it means that you program the actuator imposing a certain path or trajectory to the end effector. It means that our constraint has this form. So, oops. Has this form. The position of point P, let's call that this is point P, of body I, certain body I of the end effector, which we can always write as we have just saw like this, R0, I, P, must be equal to a certain function f, vector function, of t. Okay? So you actually prescribe that the position of point P must follow a certain path described through, let's say, a function of time. And in this case, appearance is explicit. Okay? Okay? Of time is explicit. Okay, so these are just two very simple examples of holonomic constraints. As you may have already noticed, in this case, we always constrain, as we have said, configuration of the body. So in this case, the path that the end effector has to follow. In the previous case, the position, the coincidence of the position of two different material points in the bodies. That's why they are called holonomic. Then we have non-holonomic constraints. Non-holonomic constraints constrain, limit the motion of the system. So, we have non-holonomic constraints. Okay. What form do they have? They have the following form. They have the form A0, it's a vector having nc times 1 as dimension. So it's a column vector having nc rows, which has the functional dependence over the q's, so generalized parameters, and time, plus a matrix B of dimensions nc times n, typically again function of q and time, applied over the vector of generalized velocities q dot, which, as we know, is a column vector of n rows, equal to 0. Again, remember the nc, the number of constraints, then n is the number of the q's. Okay. Now, let's observe one thing. So first of all, you have to note one thing, which is important, that neither the B nor the A is a function of the velocities. Okay, this is important. So we refer to this as, in fact, as a simple non-holonomic constraint. What does it mean? It means that you have a linear relationship with respect to the generalized velocities. There are cases, unfortunate ones, in which this relationship is not linear in the velocities, but can be non-linear in the velocities. And in that case, we talked about complex non-holonomic constraints and, as a consequence, complex non-holonomic systems. And okay, we will not treat those kind of systems in this course, but for those of you who wonder, in that case, you cannot use this simple form for the constraints, but you have to derive them and go up to the acceleration form, hoping that you will have a linear form in the acceleration in that case. But that's another story. What I wanted to show you is that we could write the following. Let's retake the previous form that we had saw for holonomic constraints, which was like this. Okay, and let's derive this in time. Okay, so derive in time. What we have, if we do the total derivative of this with respect to time, we get the following. We have the C vector. Since this is a function of Q, which are functions, so if I wanted to write it explicitly, I should write Q of T, all right? So first of all, I derive them with respect to the Q's. And then I have, of course, to derive the Q with respect to time, okay? And then I have to derive C explicitly with respect to time. That's the definition of a total derivative, no? Okay. So now you can easily see one thing. So this, I said, is an nc times 1 vector. So it means that this is an nc times n matrix, this one here. You see, because it's a derivative with respect to the nq's. Whenever you, just for you to remember, whenever you have to derive a vector with respect to another vector, the one which is on top of the fraction gives the number of the rows. The one which is on the bottom gives the number of the columns. And this is, of course, what? Mn times 1 vector. So as you can see, dimension come along together quite well. And this is, again, Mnc times 1 vector. So dimensions are respected. So let's now assume that you call this D. And that you call this A0. What do you get? You get exactly the form on top. So you get A0 plus B, applied over the Q dots equal to 0. Let me rewrite it. Okay, you see, it's just the same. So now one could wonder, why did I actually bother to introduce this form if this form could be derived from the previous one? So what is the actual difference between holonomic and holonomic constraints if the form are basically the same? Well, there is a trick, and there is a trick which is an important one. So here, what I showed is that I can always pass from this form to this form through derivation. And we know the derivation, given some hypothesis of regularity of the matrix that we can easily assume as fulfilled, can always be done. So I can always derive a function. The reverse is not always true. Integration is not always possible. Why? Because there are some functions that do not allow the definition of a primitive function. You have this concept already from analysis 1 course, the basics. So it means that can always pass from here to this, but the converse, passing from this and integrating back to this, is not granted. So let's write it. So I can always derive given, let's say, appropriate regularity condition. So I can always pass from here to this. The existence of an integral function instead is not always granted. Okay, meaning that I cannot pass back to where I wanted to be before. This is not always possible. Okay. Now, there is a way, in fact, to characterize this possibility or impossibility to pass from this form to another, and which is the use of the terms kinematic and geometric constraints. So let's just be clear on this. So when we talk about holonomic and non-holonomic constraints, we talk about something associated to the physics, okay, of the constraints. When we talk about, and we will see it right now, kinematic or geometric constraints, we only talk about the mathematical form that they assume in our problem, okay? And this further differentiation, this further terminology will help us to discriminate between these two possibilities. In this way, so we can, so we further introduce the terms one, geometric constraints. If they have the form C Q T equal to 0. 2, kinematic constraints. And they have the form A0 of Q and T plus B of Q and T. Okay, so why did I actually bother to introduce this? Because we can say that holonomic constraints can be geometric or kinematic integrable. Kinematic integrable. So I can integrate this, I go back to this. Okay? Integrable. Non-holonomic constraints they are just kinematic non-integrable. Okay? So this was basically made to possibly limit confusion. Okay? So we have really the holonomic constraints are those who constrain the position, the configuration. From a mathematical point of view, they can have this form, geometric, or this other form, but with the possibility to integrate and go back to that. Geometric, kinematic, integrable. Non-holonomic constraints are those who constrain motion, and they can only come with this form without the possibility to integrate back to that one. Okay, clear? Okay. We make an example right now so that we can clear up ideas. Can I swipe? So let's make an example of a non-holonomic constraints. Non-holonomic constraint. To do so, we consider, here you go, the case of a spinning top. Trottola, una trottola. So what I want to do with this spinning top is to enforce a condition on the velocity. Okay? You see, I'm enforcing a condition on the motion, not on the configuration. That's why it's a non-holonomic constraint. So I want to enforce a condition on the spinning velocity of the top. Okay, velocity, please. If you remember, the velocity, the angular velocity of a body, we saw it last week, given with respect to the body frame, could be written as such: G, using Euler's parameters, over bar I, and the vector of Euler's parameter, theta dot I. So this is, again, for those of you who do not remember, theta dot I is nothing else than the column vector theta 0, theta 1, theta 2, and theta 3. I. Okay. I want that omega I, this again G I theta I dot, must be equal at all times to a function f, vector function, which is a function of what? Of the q and t. Now, if you already watch this, you can notice that it has the form of non-holonomic constraints. Why? Let's say that I pose that my q dot I is my theta I dot vector, that my B I matrix is my G, and my A0 vector is minus F I of Q and T. Okay, so that eventually my equation becomes exactly A0 of Q and T plus B of Q and T applied over Q dot equal to 0. See, that's exactly the form that we wanted to see. Just enforcing that the velocity, the angular velocity, the spinning velocity of my top has a certain law. Now, let's now try to answer to another question. We have seen, if you remember, it was I think on Monday, that the number of constraints reduce the number of parameters that I can set freely. We saw it with the calculation of the degrees of freedom. We will define them later on. For the Poisselier mechanism. Now the question is there any difference in terms of reducing the number of parameters which I can set free when I consider holonomic and holonomic constraints? So holonomic constraints, they limit the configuration. Non-holonomic constraints, they limit the motion. Do they have the same effect in reducing the number of parameters which I can set independently from all the others? What do you think? Holonomic, we constrain the position and the configuration. Non-holonomic, the way the system moves. Is it the same in terms of reducing the number of independent parameters which I can set to describe my system? Let's find out. Okay, have you ever thought about this? All right, let's see. So an example. Okay. Our example is constituted by a coin, simple coin, which is tossed on the floor. Okay, so we have a coin. We just toss it on the floor and let it roll. And we want just to enforce the fact that this rolling motion of the coin over the top, over the floor, takes place without sliding. Okay? For you to know, this is the most, let's say, typical kind of non-holonomic constraint that you can find. So imposing that something can roll over something else without sliding. That's the typical non-holonomic constraint. Okay. If you think about it, it makes sense because it limits not the position, but the way the motion must take place. It has to roll, it can roll, but without sliding. So it's a non-holonomic constraint. Okay, so example again. It's a coin tossed over the floor without sliding. So there must be some friction at some point. Okay, so if you look at this picture here, we have that. Oh, I see that there is something missing. Okay, let me just. Okay, we can just rewrite it. So this is B2. Okay. All right. Then there is the vector which defines the position of a point here, this vector here, and this point is point P, which is exactly the point of contact between the coin that you can assume to be as a disk, so with zero thickness, for the sake of simplicity. So this is the point of contact. This is, of course, typically our origin, O prime. We call it O prime for the local frame. Then we have that this angle here between the vector going from the origin of the coin to the contact point and the axis B2, which you can call phi. And then we have another angle, the angle formed. Please do not confuse it, but I know it's not super easy to do so. Let's call it with this. Between the angle B2 and the vertical, the normal, okay? And we call this angle capital phi. Okay. I think that's all. Yeah, wait. We also have, of course, the last vector here, which is the vector, the position vector of the local frame, R. So this is basically. R. Okay, and let's say that the radius of the coin is A. We call it A. We don't know how much it is, but we don't need it. So the condition of rolling without sliding, how do we enforce it? We enforce it saying that the velocity of point P, how much is it? So the relative velocity between the contact point of the coin and the ground, which is our inertial free, must be 0. But the relative velocity in this case, since we are talking about the ground, is the global velocity. Okay? Do you see the difference? So if you happen to throw this coin over a plate which was moving over the floor, the condition of rolling without sliding would have been enforced just via requiring that the relative motion, the relative velocity between the coin and the plate should be 0. Okay? So in that case, that would not have been the global velocity, but just the relative velocity. In this case, our second body is the ground. Okay? So this relative velocity is in fact the absolute velocity of point P. And that's why here we call P equal to 0. Okay, and we will express this as a global velocity. Okay. So again, we make use of the Euler's angles capital phi, C and phi about the local axis B1, B2, and B3 to describe the motion. So we have to enforce two things if you think about it. We have to enforce that the coin touches the floor, and then that it touches it without sliding. So let's do this, constraint one step at a time. So first, we enforce that the coin touches the ground, the floor, Therefore, write that R3, if you remember, is the vertical component of the position vector of the origin of the body frame with respect to the global frame. So it's the projection of R with respect to x3. That's what R3 is equal to what? Is equal to the radius A times the cosinus of capital phi. Because capital phi is the angle between B2 and the normal. Okay, so when capital phi is 0, B2 is aligned as x3, and R3 is equally A, the radius. Okay, so A cosinus of phi. As you can see, this is a what? Holonomic or non-holonomic constraint? Holonomic constraint, the position. Let's write it actually. Then let's enforce that our motion happens without sliding. Let's do it like this. Okay, rolling with no sliding. Okay, we have already said it, that this should take the form P dot equal to 0. And since this is expression of a position in the global frame, we can write it as such R plus A applied over omega vector product R0P. Equal to 0. This form here, we have seen it last time. And this, just for you to know, this vector here is basically O prime P. This is what it is. It's O prime P. It's basically going from here to the contact point. Okay. Okay, so let's write it. We saw that omega is equal to G applied over theta dot with G being the following. Cosine, if you remember when we described the Euler angles parametrization, we also enforced this when we characterized the series 3 sequence of rotations about the 3 axes. So if you do this, since here we are characterizing a rotation basically of these triangles about the axis B3, we can already say that this has the following form. Psi, cosines of phi. Let's actually take a little bit more time. Sorry, space, like this. So, cosinus of psi, cosinus of phi, sinus of phi 0. I will not ask you to demonstrate this, but you can already intuitively understand why this has this form. Oh, but wait a minute, here I had a lot of space. Okay, all right. Well, doesn't matter. Cosinus of psi, sinus of phi, cosinus of phi 0, and then we have the sinus of psi 0, 1. Again, why does this have this form? Because it's rolling about the angle B3. And if you remember, at the very start of this exercise, we said that the three Euler's angles that we were about to use were referred to three successive rotations about B1, B2, and B3. Okay, so that's why here we have this form with 1 at the end. And of course, in this definition, we have that in this case, theta dot is nothing but the vector of the Euler's parameters derived with respect to time. Okay. Okay, so if you consider, let's try to see, okay, the coin from the perspective of B3. If we do that, we can draw it like this. This is our floor. This is our coin. Should be round, but it is not. Here we have B2. Here we have B1. Here we have O prime. And B3 basically comes out of the board. Okay? And here we have basically our point P. Actually, let's write it with another color so it's more evident. This is our point P. Okay? So from here we can write that our vector R0P can be written as such. Allow me to just make a small modification. Sorry. Because otherwise it's not super clear as it should be. So let's actually give a little bit of tilt. This is still B1, this is B2, and this is still B3. Okay. And this okay, that's why I did it. That's the angle phi as we have defined it. Okay. And remember that this quantity is the radius alpha, A, sorry, is A, the radius. Okay, so R0P, which is the position of point P in the local frame, the body frame, has the following components: A, sinus of phi, minus A, cosinus of phi, and 0, no projection over B3. Okay. Okay, so again, it would be this one, just for you to be clear. It would be this one. So this one and this one, okay? And this one here. All right? Okay. Now, so let's write finally our, can I slide? Let's write finally our condition. So the condition P dot equal to 0 becomes again R dot plus A applied over omega vector R0P and therefore from here we can write R dot equal to minus A applied to omega R0P, and therefore eventually we have, from a vectorial point of view, R1, R2, R3 dot equal to what? Let's say we just put everything together, A, which is the radius, applied over phi dot cosinus of psi, psi dot sinus of psi, without the dot, plus phi dot sinus of capital phi, sinus of psi. And then we have minus psi dot, the cosinus of psi, minus phi dot, the cosinus of capital phi, sinus of psi. Okay? Now, we can just rewrite this, putting into evidence the angular velocities. So I put, let's say I can rewrite R1, R2, and R3 as, again, A multiplying 0, 0, cosinus of psi, sinus of psi, 0, sinus of phi, capital Phi, sinus of psi, minus cosinus of psi, 0, minus cosinus of phi, sinus of psi, applied over dot, phi dot, capital Phi dot, psi dot, and phi dot. Okay. Sorry, and here, of course, there are dots as well. Okay. Now, if I want to write all of the Q dot, all of the Q dot, allow me to write it like this. So here I have phi dot, sorry, capital Phi dot, psi dot, and phi dot. The only thing that I have to do is the following. 1 over A, 0, 0, 0, 1 over A, 0, 0, 0, 1 over A. Okay? I just wrote an identity. I added an identity to my system of equations. That's what I did. I wrote that this is equal to this multiplied by this. Please take into account that there is a name multiplying here. Okay? So what I'm writing here with the last three are just an identity. Okay, I didn't add anything, in fact. Because I multiplied this by this and this vector here, I got an identity. So I added no information. All right. Now, allow me to do another stuff. Okay? Allow me to multiply the left hand of this equation and the right hand of this equation by dt. Okay, the total differential of time, dt. Okay, what do I get? So this, for example, r1 dot can be written as what? As dr times over the t. Okay, that's by definition. So I want to multiply by the t both members of the equations. So what do I get? I can cancel this and write d. Okay? You see what I'm doing? Okay. I do this, I do this, I do this. And of course, I have to do the same on the other hand. So I get the phi, the psi, and the phi. Okay? Why did I do this? Because this, you can see, is the Q. You see, it's the vector of generalized parameters which completely identify my system. The three let's say, components of the position of the origin, and then the three Euler's angles. And these are the three Euler's angles. So what I can say here is that the condition of imposing rolling without sliding eventually imposed what? That we can only have, sorry, 3 independent variations out of 6 parameters, okay? Meaning that the condition of rolling without sliding translate into imposing how many conditions on the parameters? If only 3, you see, only 3 I can set free, and all the rest come as a consequence. So how much do they count in terms of reducing the number of coordinates? 3, right? 3. So I have 6 parameters. I have one scalar equation, holonomic scalar equation, imposing that the coin touches the floor. And then I have additional 3 non-holonomic equation that you see govern the way, not the exact value of this parameter, but the way they change. You see the variation, the delta, how they progress in time. But they still enforce 3 equations, so that eventually from 6 independent parameters, I'm down to 2 independent parameters. Because I have 3 conditions on the variation and 1 on the position. Okay? Is it clear? So now the original question was, okay, but here, in fact, I'm not really constraining the exact value of R1, R2, R3, and so on. I'm constraining the way they vary in time. It's not really the same, is it? It is not. But it becomes identical when we, in fact, assume and associate to this problem one additional information that we need to close it. When we have a problem, a dynamical problem, which encompasses the description of a system, the behavior of the description of a system in time, what do we need? We need boundary conditions, as as it is typically, but we also need initial condition. And if we impose an initial condition to these variables, and we impose the way they must vary in time, we basically impose their exact value in time. Because if we say, look, you have to start with this value, and then we say, look, you have to vary in time following this law, we have set everything for that variable. Is that clear? So that's why eventually non-holonomic constraints, basically, even if they do not directly, in fact, impose the value, the exact value, the punctual value, the pointwise value of the variables of the system, but only their variation, when they are considered in association to initial conditions, which is a piece of information that we need to close the problem, they have, in fact, the result of valuing or having the same exact value of holonomic constraints in reducing the number of parameters that we can set freely to the system. Okay, so what we can eventually say is that only 3 parameters, namely phi, capital Phi, psi, and phi, can vary freely. And so this means we impose 3 conditions on motion. Plus 1 condition on configuration. We have eventually 4 constraints. Equations. And from this, we have eventually that only 2 out of the 6 parameters R1, R2, R3, the phi, psi, and phi can be set independently or freely if you want. Okay? Okay. So what we have seen so far is that, okay, constraints limit the number of parameters describing the system, which I can set freely. Okay, no matter if they are holonomic or non-holonomic. Eventually, in this count, which is also referred to as Grubler count. Have you ever heard this definition? Okay, when you basically have the total number of parameters minus the number of linearly independent constraint gives you the number of degrees of freedom. That's called the Grubler's count. Okay, whatever. But so, can I actually make use of this difference between parameters which can be set freely and parameters which just follow from the independent ones through the constraints? The answer is yes, you can profit of this. And in fact, you will profit of this when you will try to encompass your constraint equation into your equations of motion. Okay, you will do what is called partition of the generalized parameters between independent and dependent ones. Okay, so that you will be able eventually to express the dependent parameters in terms of the independent parameters via the constraints. So what we will introduce right now will be the so-called coordinate partitioning. Okay. Okay, so let's say that we have NC constraint equations. Please do not get confused. I actually also tend to do this mistake often, while I speak. But please try to have in mind the difference between the number of constraints and the number of constraint equations. It's two different stuff. And C is the number of constraints equations. What is the difference? Well, one constraint that we saw in the previous example, which is the condition of rolling without sliding, eventually implied three scalar constraint equations. Okay, so the number of the constraints and the number of the constraint equation which describe those constraints are two different things. Okay, and C is the number of constraint equation. And C constraint equation and NB bodies in 3D space. So this means that we have NC dependent coordinates each one for each constraint equation, and we call it QD with the subscript D, and this is a column vector having NC times 1 as dimension. And then we have N, which is, let's say, 6 times NB. That's the total number of parameters. So we have N minus NC independent coordinates. And we call them QI, of course, which has dimension N minus NC times 1. Okay, this is always true both for holonomic and non-holonomic constraint. I didn't specify so far if this constraints equation and C were holonomic or non-holonomic. So this partitioning can always be done. But now we specify eventually our case. Let's assume that our constraint can be written as such. C Qt equal to 0. Okay, so this is an important limitation because it means that we are only referring to holonomic constraints. Again, or said differently, geometric plus kinematic integrable. Okay? So this is an hypothesis that I'm doing, a strong one. It's a limiting hypothesis. Okay. So I'm basically just assuming that we are talking about holonomic constraint. And let's assume that my system undergoes a virtual displacement. The system undergoes So what is a virtual displacement? The virtual displacement is, what does it mean? The virtual displacement is a displacement which is infinitesimal and which is compliant with the constraints, meaning that I am considering as a virtual displacement a displacement field which I superpose over my system, which is infinitesimally small and compliant with the constraint. Okay, so that we have before the motion, before the virtual displacement, we have what? Q0, sorry, C, which is again my vector of constraints, which is a function of our generalized parameters Q0 and time equal to 0. Sorry, let me just, this is really in the middle of the way. Okay. So this is the first form, and then there is the second form, which I call C1 of Q1 and T. What are Q0 and Q1? So my virtual displacement is delta Q, which is nothing different from Q1 minus Q0. Okay? That's my virtual displacement. Q0 is the value of the generalized parameters which describe my system before the virtual displacement. Q1 is the set of generalized parameters which describe my system after the virtual displacement. The virtual displacement is given by the difference. Okay? So, given that we have this before and after condition, I can rewrite my constraint equation before and after the virtual displacement. And since this virtual displacement must be compliant with constraints, they both must be satisfied in both conditions, before and after. Okay? So the before, after the virtual displacement. Okay? So that I can also define the delta virtual variation of the constraint given exactly by C1 minus C0. Okay, so what is it that I want to go from here? And then eventually we are almost the end of our lecture. If this is true, we have that, let me write it, by the definition of C0, C1, we can write that delta C is equal to, of course. And therefore, if I derive you have dc over dq times delta q is equal to 0 as well. What is this? Can you guess? You should have seen it so many times already. This is what I call, this is a matrix. We saw it. This is a matrix which is nc times n. And it's called the Jacobian of the system. We call it, CQ. CQ. It's a matrix. We call it Jacobian. Jacobian of the constraints. And this has a form, and then we are basically done. Like so. You have C11 going to C1n. And then we have this going to CNC1 to CNCn. So, again, this is nc times n. This matrix so this is a rectangular matrix, not it typically n, remember that n is typically larger or equal than nc. Okay, so what is the highest rank that this matrix can have? nc, right? When is it that nc is exactly the rank of this matrix? Can you guess? So this is a rectangular matrix that we call Jacobian of the constraints, which is a rectangular matrix, and which can have at maximum NC as rank. When is it that it has NC as rank? So the rank is the maximum possible. Exactly. So when all of the different rows are independent rows. Well, when is it that they are independent rows? What does it mean that they are independent rows? That what is it that are independent? No, the constraint equations. Okay, basically the rows are the coefficients of our constraint equations. So this has full rank of NC if the NC constraint equations are all linearly independent. Okay, and this is a super important fact. Okay, now next time, which is tomorrow, we're gonna see what is the meaning of this and why this is important. I can anticipate it already to you, saying that if these are all linearly independent, we can make use of this, let's say, matrix or some decomposition of this matrix to express the dependent constraint, the dependent parameters, coordinates, in terms of the independent ones, so that eventually, given this relationship, we can use this relationship in our equations of motion and have equations of motion given only in terms of the independent parameters. And that's why we'll see it, these Lagrangian parameters are important, because eventually when we do so, our equation of motion will be written only in terms of independent parameters, and we will not see anymore any constraint equation. It's done once and for all. Okay, but we will see this next time.